Okay, so we're going to talk about the intermediate value theorem today.
Oh, gosh.
Okay, it's so important that it's got a name. So that means that this is probably a good theorem to know, okay? Intermediate value theorem. Sorry, yeah, my handwriting there is a little sloppy, but okay. Okay, and yes, this is an important theorem, okay? In fact, it's used throughout calculus, and it's mainly shows up as a justification in some of our free response questions, okay? So I don't think that we need to be able to name it necessarily right now, but we do need to understand the concept of it because it's very important, okay? So to do that, though, to introduce the idea, we're going to do a little consideration. So consider f of x equal to the polynomial function x to the fourth minus 6x plus 2, and we're only going to consider it on a particular interval 1 to 2. Okay, because the intermediate value theorem is over an interval. It's well, I guess it is. Let me see here. Yeah, on a closed interval. So that's why we're starting on a closed interval here too. Okay, so there's that. So we're considering it right now, right? You guys are thinking about it in your brains as you're writing it down. All right, so the first thing I want you guys to do is take like 2 seconds and find f of 1 and f of 2. And you may use your calculators if you want. Okay, but go ahead, take 2 seconds and find the function value at the left end point of the interval and find the function value at the right end point of the interval. Okay? So again, take 2 seconds and go ahead and do that. Once you finish writing everything down, because I'm sure you're all busy doing that too. Okay, time's up. Tyler, what'd you get for f of 1? Negative 3. So when I plug in x value of 1, the function gives me a y value of negative 3. Okay? Great. And let's go to Emma. F of 2, what'd you get? Can you do pass? All right, this time. Austin, what you got? 6. Okay, so there's our answer. 1, negative 3. So when I plug in the x value of 1, I get a y value of negative 3. When I plug in the x value of 2, I get a y value of 6. Okay? So you're like, great, Mr. Whitmire. We've seen this since probably elementary school. Okay? So what I want you guys to do is explain, and you don't have to write it out if you don't want to. You can just like think about it in your brains. But explain why you think f must or must not cross the x-axis somewhere between x equals 1 and x equals 2. Okay, so think about that. You can explain. When I say explain, just like think about what your explanation might be. Why f either must or must not cross the x-axis. Or in other words, will f cross the x-axis based on this information that we have right here? Okay, and if you think it must, think about why that is, or maybe you don't think we have enough information yet. Okay, if that's true, then that's okay. That's a possibility as well, right? So must f, based on this information, cross the x-axis? Can you make that argument here? Okay, so someone want to volunteer here? Yeah. So let's go to Tyler.
All right. So it is f of 1, but the x value of 1 is negative 3.
Okay. Y value of negative 3. Mm-hmm.
X equals 2.
Mm-hmm.
Y value is 6, so it has to go across the x-axis.
Has to go across the x-axis. So if I were to, kind of like imagine here, right? If I just do a quick sketch, I have the point 1, negative 3. Bless you. So there's the 1 point. Bless you. And then at 2, it goes up to 6. And we know that we had to go from this point to this point. Right? We got to go from here to here. And so it looks like it's got to go through the x-axis, right? Right, go around it. He's like,
And you did.
So, touche, Mr. Widmeyer, touche. All right, so anyway, so that's obviously still going through the x-axis there, right? All right, so there's that. Great, good job. All right, so we kind of see there that because we're going from negative to positive, basically, we got to go through that x-axis. All right, so now let's consider another one. Consider g of x, piecewise. X squared plus 2 for negative 3 less than equal to x less than equal to 0. And it's equal to 2 minus x cubed for 0 less than x less than equal to 2. Okay. Okay. So I want you to find g of negative 3 and g of 2. Okay, so go ahead and take 2 seconds. Find g of negative 3 and g of 2. All right, so Chanda, you got g of negative 3 for me?
Yeah.
All right, what you got? 11. Very good. Okay. And then go ahead and give me g of 2 as well, please. Oh, yeah, okay, you didn't get that one. So which one are we going to... What's that? Negative 6. Very good. Very good. Okay. Okay, so again, we had x value of negative 3, okay, gave us a positive 11 value, and then x value of 2 gave us a negative 6 value. So, again, my question, similar to the one before, must g of x equal 0 for some x value between negative 3 and 2. So must our function equal 0 for some x value between negative 3 and 2 based off our information right there. Okay. So okay, I hear some yeses. Anyone care to explain here? So Ryan, what do you say?
Well, it's pretty much asking if it crosses the x-axis.
Mm-hmm.
And yes, because it goes from a positive to a negative.
So if we go from a positive value for our function g at negative 3 to the negative value of our function g at 2, and so to get from here to here, we have to go through 0, is what you're saying. Okay, Brandon?
It doesn't have to equal 0 because, I mean, I know it does cross 0 and does equal 0 at one point, but with the information given, we can't conclude it because it ends at 0. It's equal to 0 at one point. X value is equal to 0, so there could be a jump at that spot.
Ah, so if our function is not continuous, we could have a problem here. Well, let's maybe see if it's continuous. What's that?
What it does.
Well, yeah, I know it can, the question was must, and with the information there, it doesn't happen.
So let's take a look and see here. Let's take a look and see. So good thinking here. We could have a jump, right? And if we have a jump, then all bets are off. So let's see here. Now, to graph a compound inequality like this, when you go to divide, this is like kind of crazy, all right? But you have to break this thing up. You can't write the compound inequality as you see it there. You have to break it up into 2 inequalities and then use the AND command on your calculator. So I'll just show you how to do this real quick. Okay, so we can type this one in. So negative 3, second test, sorry, less than or equal to x. Okay, so I'll type the left-hand side of that inequality in. But then I also have to use the test. I have to go over to logic and use the AND command. Yeah, there's an actual AND command, yep. Yep, not ampersand, ampersand, anything like that. Okay, and then we'll do the other test value. X is less than or equal to 0. Okay, and those again from Steinfeld's class, this is how we do piecewise, this is how you can graph piecewise functions, okay? Yeah. I know you guys didn't really use your calculators that much, right, in the class. Okay. You didn't use them at all. Okay, so here you go. Okay. This one you don't necessarily need to follow along with, but in the future I would suggest anytime we do a calculator thing, if you want to follow along with this one, it wouldn't be a bad idea. Just because not only you can see it up here, but also for you guys, using the calculator is kind of like a skill unto itself. And so just being able to type things in correctly and all that is important. So if you have it, I would suggest getting it out and just following along. Okay. And then divide by, and then we'll do this one. So 0 math. I hope this works. I think I typed it in everything. I think I'm telling you guys what's right here, but
I hope so too.
I don't do the compound inequalities very often. It does work. Hallelujah. Okay, so it did work. Neat.
Cool beans.
Cool beans. Beans.
What's the button to get to like the less than or equal to?
So second math gets you the test. Okay, so real quick, just for my Steinfeld kiddos again, okay, when you graph a piecewise function, just like a little crash course here, you graph the individual parts in your y, so first one goes in y1, second one y2, so on and so forth. Make sure you put parentheses around it, and you're going to divide by, and then you divide by the argument, or whatever this inequality is here, okay? To access these inequality symbols, you press the second math button, takes you to the test menu, there's your inequality symbols, and then if it's compound here, you got to split up into two inequalities and put an and between them. Okay, so it ends up looking like this. -3 less than or equal to x, and x less than or equal to 0. And then 0 less than x, and x greater than x less than or equal to 2. Okay, and when you graph it, it gives you a nice piecewise function. Now, bless you, this piecewise function, does it have any jumps? Does it go through 0? It does, so this one's okay.
Well, it's not necessarily pertaining to this, but when would you ever use an XOR inside of it?
Sorry?
The exemption of OR, like where...
I don't know, but you can program the calculators too. So I mean, there are times when you would do it, but I can't think of it for the inequalities. I don't know. I don't think you use it for like piecewise stuff, no. But definitely you can program your calculators, and I'm sure it would come up in that for certain. Okay, that's great. So the answer is yes here. It must. Because the function is continuous. One more.
H of x.
H of x. Consider h of x. So slight change here. The arguments are still the same from before, but the slight change in the piecewise function. Okay? So if you saved your piecewise function in your graphing calculator, this will be helpful. We can like graph it, and we'll just adjust things, or if you cleared it out, though. Womp womp. Okay, so same deal as before. I'm going to have us find the value of our function at our endpoints. So we'll find h of -3, that's the left endpoint of our piecewise function, and I also want you to find h of 2, that's the right endpoint of our piecewise function. So go ahead, please find those two things. So it's not quite the same function, is it? The top piece is, and the arguments both are, but the second piece there is not exactly the same. Slightly changed. Okay, it's good. I'm glad that you're looking out for that kind of stuff. That's good observation. Okay, so take 2 seconds. Okay. So again, h of -3. Okay. What's h of -3? Okay, so I'm going to go to Josh. Did you get h of -3? 11? Yeah, again, right, because it's the same thing as before, so yeah. Surprise, surprise. And do you have h of 2? So -2 minus +2, -4. Yep, very good. Okay, so again, we end up with our left endpoint having a 11, y value of 11. Our right endpoint has a y value of negative 4. So my question to you then is, must h of x equal 0 for some x value between negative 3 and 2? Must we equal 0 here? It went from a positive 11 at negative 3, x equals negative 3, was at positive 11, and then at 2, it was now at a negative 4. Must our function then equal 0 at some point? We went from positive 11 down to negative 4, must our function equal 0?
No. There could be a break.
Why not, though?
There could be a discontinuity.
It goes from positive to negative. Yeah, there could be a discontinuity. And in fact, let me go back to my graph here. So if I adjust my y equals, the top one's going to stay the same, y1 stays the same, but this is going to be negative 2 minus x. I got to delete all this other junk out here. Okay, graph it. Whoa. Does our function h ever equal 0?
No.
And why not? Because there's a discontinuity. Okay, there's a jump there. Okay, so it fails here, even though this one makes sense, right? Because but what's true about this function?
There's no ability for it to be discontinuous.
Yeah, this function is continuous on this interval, right? There's nothing funky. It doesn't jump. It doesn't break. There's no asymptotes. It's just a normal kind of polynomial function. So on this interval, it's continuous. Therefore, we can say that it must equal 0. Here as well, what was true of this piecewise function? Was it discontinuous on our interval from negative 3 to 2? No, they joined up, right? At 0, right? This is 2, and this also has a value of 2 at 0. So these 2 points join up. There's no jump, gap, break, asymptote, whatever. It joins up, and so therefore we're able to say that yes, it does equal 0 from between negative 3 and 2. Here, though, even though between negative 3 and 2 we go from an 11 down to a negative 4, going through 0, right? This function, is discontinuous. And so we're not guaranteed for it to equal 0. In fact, in this case, it does not go through 0. It jumps. Comes down here, jumps down to that. Okay? So the answer is no. Because h is discontinuous. On the interval from negative 3 to 2. Okay? Now, I want to be very careful here. You could still equal 0. Obviously not in this function. But if all we're told is that our function is discontinuous on our interval, it still could potentially equal 0, for example. But we're not guaranteed for it to equal 0. Okay? We're not guaranteed for it to equal 0. So it could equal 0, but we're not guaranteed it could equal 0. Even though it goes from a positive 11 down to a negative 4 or whatever. It could. But we're not sure. Okay. Not guaranteed. So, that is the basic idea of the intermediate value theorem. Okay, that's kind of like the basic understanding of it. So let me go into then the definition, the formal mathematical definition. Okay, the idea of the intermediate value theorem, okay, is essentially this. So I'm going to write that. Oh, you can't see it, sorry. There we go. Intermediate value theorem. Okay? This theorem, along with like the definition of continuity, is something you should know. I'm not going to ask you to like regurgitate it on the test or something like that, or on a quiz. I won't be like, define intermediate value theorem, okay? But you better be able to apply it. And by understanding it and knowing the definition, you will then be able to apply it better. Okay, so it's something you need to know. Just like you need to know the 3 properties of continuity. What are those 3 properties again? The limit as x approaches c of the function exists. So the limit exists. The function f of c must exist and go to a value. And the limit and the function must have the same value, must go to the same value. Okay, so again, limit exists at the point, the function exists at the point, and the limit and function must have the same value at that point. Okay, so f of c must equal the limit as x approaches c of f of x. Okay, so don't forget those. You need to know those. Okay, those of you guys that don't know, Miss Wood, I don't know how to study for a math test. That's how you study. You go back and you read the definition and you remember it and you make sure you understand it. Same thing is true here for intermediate value theorem. suppose f is a continuous function, right? We saw before that it's so important for us to have a continuous function on the closed interval. Someone's blowing up over there. It might be me. I don't know. I hope not. That's not what I sound like, though. Is that?
Sorry.
Okay. Toot.
I can't see.
Sorry. Thank you. Awesome. Okay. Suppose f is a continuous function on the closed interval AB. That's important. Must be continuous. For any number k between f of A and f of B, there exists a point C between A and A and B such that f of C equals K. Okay, now I'll let you guys finish writing that down, and then I'll kind of describe it to you in more plain English. I'm going to give you the mathematical definition, okay, because that's where we are. This is AP, right? This is what we're supposed to be doing. This is college level. This is what college professors will be writing down on the board. Okay? But because we're also in high school, I want to make sure that I help you transition that understanding as well. Because college professors would be like, all right, moving on. And you'd be like, what? And then you go and ask your TA, and if they help you, maybe. But sometimes they don't help you too. Just speaking from experience, okay? So anyway, there's the mathematical definition. So going back, how does this incorporate to what we just did, Mr. Whitmire? This makes no sense. Okay? So, going back to our first example, f is a continuous function, right? We kind of established that. It's a polynomial, there's no jumps, no gaps, no holes, okay, none of that, no asymptotes. Nice, continuous function. And it's on a closed interval from 1 to 2. Okay? We found f of b and f of a, negative 3 and 6, and so then we were able to say that because we go from negative 3 to 6, we must go through 0. But not only must we go through 0, what other y values must we hit? Not just 0, what other values of our function must we hit?
Like 1.
Yeah, we should be able to hit negative 2. We should be able to hit positive 1. We should hit 5, 4, 3, 2, 1, okay? All those numbers, those are k numbers, okay? Any number k between your two function values. So our function values here are 6 and negative 3. So any y value between 6 and negative 3, we should hit. And what do we mean by we should hit? There should exist a point C between 1 and 2, such that f of c, when you plug that c value in, you get that k value you're looking for. So for example, if Max over here and say, Mr. Whitmire, must our function equal 5? I'll say, well, 5 is between negative 3 and 6, and so there must be some c value between 1 and 2 that when you plug it into the function, gives you a value of 5. Okay, and that's it. That's what the intermediate value theorem says. So you might realize, though, the intermediate value theorem does not tell you where it is. It just says that it exists. So this does not say, how to find that point. It just says that that point will exist. So I know between 1 and 2, my function value will be 0 because it goes from negative 3 to 6. I don't know for what x value that is, though. It doesn't tell you what the c value is. It just tells you that that c value exists. Okay? So this theorem is mostly an existence. It just tells you that it must exist. It does not say what that actual c value is. We can maybe figure it out. Sometimes we can't. Okay? That's part of our analysis. Sometimes the most powerful thing we can say is that, it must equal 0. But we won't be able to say where it necessarily equals 0. Okay? So, that's intermediate value theorem. Alright, so, let me give you guys a little example here. So, of f and g are given below. The function h is given by h of x is equal to f of g of x minus 6. Okay? And in parentheses I'll put here f, g, h are all continuous. Okay, and here's the certain values of fg that I promised. Sorry, here you go. Okay, so this is all set up, right? There's no question yet. All I've done is just giving you a bunch of information there. So then our actual question, or our actual task, is to explain why, and I'll already kind of explain why there must be a value R between 1 and 3, such that h of R equals -5. Okay, and I'm not gonna have you guys do this on your own. Okay, I'm not gonna have you do it on your own. We're going to do this one together, but there's the setup. Okay? And you might be like, Mr. Meyer, why are we setting it up this way? This seems like way different than the stuff we talked about before. Well, sometimes we're given information in a table like this on the AP test. Okay? It's a popular way to kind of sometimes give information. Okay? We can read tables, and we just need to pull out our necessary information here. You'll notice we're not given what f and g are. We're not told what the function f is. We're not told what the function g is. Okay? We're told what h is, and h is like related to f and g. Question?
How does it work? Because -5 isn't like a point on. -5 doesn't look like it's between anything.
Right, and so we don't have to find. It does not say find the value of r such that h of r equals -5. We just have to explain why there must be a value r such that h of r equals -5. So we need to just show that some r exists that would give us -5. We don't actually have to find what the value is. Let me show you. Okay, we're going to do here.
I'm just confused. How do you know that something equals -5?
Great question.
-5 isn't between 1 and 4 and -5.
So hang on just yet. We have to find h here. So let's take the endpoints. Where did I put my colored pen? There it is. Okay. So let's go ahead and evaluate our endpoints here. So let's evaluate h of 1, because that's the one endpoint for our interval here, right? Our endpoint is 1. And I guess I'm going to, so I make these inequality symbols equal to's. Okay, but let's go ahead and evaluate h of 1. Okay, so this is like bringing back some stuff we talked about in the past with like, function within a function kind of stuff, right? Okay, so let's see here. That's going to be h of 1 is equal to f of g of 1 minus 6. Okay, f of g of 1 minus 6. So let's see here. So Anna, what's g of 1? 2. Very good. And then Anna, what's f of 2? 9. And then 9 minus 6 gives us 3. So h of 1 is equal to 3. Okay, good. All right. Emma, what about, let me get this one. So let's find h of 3. We'll do f of g of 3 minus 6. So Emma, what's g of 3? 4. Okay, and is everyone okay with how we're getting these numbers? Okay, so yeah, it's 4. And what's f of 4, Emma? -1. So -1 minus 6 gives us h of 3 is -7 then, yeah? Okay. So again, let's look at our results here. What are we trying to show? We want to explain why there must be a value r such that h of r is -5. And the r value is going to be between 1 and 3. We went ahead and evaluated our endpoints here. We found h of 1, we found h of 3. h of 1 was 3, h of 3 was -7. So I know we already kind of assumed that it is true, but must h equal -5 on this interval? Yes, it goes from 3 to -7, right? So it's got to hit -5 because that's between these two. Okay, that's the idea of the intermediate value theorem. But wait a minute, we saw before for this third piecewise function that that's not always the case because in this case the h was discontinuous. Why is it okay to say that yes, it's going to hit that -5 here?
You define that f, g, and h are all continuous.
Yeah, it's right up here. F, G, and H are all continuous. So there's no jumps, gaps, holes, asymptotes, okay? It's just these two, okay? So it's going to be nice and continuous through there. So if we start at 3 and we get down to -7, that means we have to go through 2, 1, 0, -1, -2, -3, -4, -5, -6, and then finally down to -7 there, okay? So that's kind of the idea, but then how do we verbalize that? How do we write that out? Okay, and this is something we're going to have to practice as well because there are times when we answer free response questions and we need to actually write a little sentence as an explanation for our justification. So here's what I think is a good explanation. Okay, since -5 is between h of 1 equal to 3 and h of 3 equal to -7, and then we put in parentheses, and f, g, and h are continuous. Okay. It's going to kind of starting, you notice the intermediate value theorem, how do we know we can use it? F must be continuous on the closed interval AB, and then for any number k between f of A and f of B. So I'm kind of like, I'm building into that intermediate value theorem. I'm starting with that. -5 is between our y values of our two endpoints. And I'm also asserting that f, g, and h are continuous. Again, kind of just like building into that intermediate value theorem, okay? Then, by the intermediate value theorem, since we've kind of checked off those necessary things, we can say by the intermediate value theorem, okay, and I would not abbreviate that in an explanation just because I'm not sure that the graders will, be okay with that. There must exist an R between 1 and 3 such that h of R equals 5. -5. Whoops, -5. Okay? Ms. Widmeyer, intermediate value theorem says that there must exist a C between A and B such that f of C equals K. C, R, it's a variable. You don't have to use, it doesn't have to be a C all the time. Okay, here we're using an R because that's what we use in the problem. Okay? But the principles still apply. The function's continuous. The left and the right endpoint, okay, we get their values, and we see that the value we're looking for is between them. So therefore, there must exist some value R between 1 and 3 such that h of R equals -5.
So if we write all that out on the free response question, should we also do the work for both h of 1 and h of 3?
Yeah, because that's part of your justification. I think, well, I don't know. If you show this, then technically that's like showing that you found those values.
I mean, I guess you're going to have to.
Yeah, exactly. So it's part of it. Okay? So, any questions on that? Okay, so yeah, so let me get you guys the assignment first, right? Homework more important than donuts.
How about that?